Hello everyone, I'm Yo. Today I represent OmniSense, exploring novel input sensing and interaction techniques on mobile device with an omnidirectional camera. This work is done in collaboration with many co-authors, as listed here. Currently, using touchscreen on mobile devices still has some limitations, such as the fat finger problem, one-handed problem, and 2D only. On the other hand, wide-angle lenses are getting more and more popular nowadays on smartphones. Furthermore, 360 degrees cameras are getting more and more popular as well. In fact, there are some smartphones with built-in 360 camera as shown here. In this paper, we explore an all-in-one sensing method for improving mobile interaction by leveraging this built-in 360 camera. As you can see here, 360-degree camera captures an all-round view around the device. It provides a complete understanding of the visual world and context around it. It includes the user hand, grip, finger, body pose, face, and the surrounding environment. We explore the broad design space for mobile devices with built-in omnidirectional camera, and we also explore the potential use case and applications that leverage these sensing capabilities. Here are some examples of the sensing capabilities. Here, we can see the full 360-degree view, and if we focus on the frontal part, it can see the approaching cars. Or it can also see which hand is holding the device, or both hands, or it can also recognize which finger is hovering above the screen. On the right side, it can detect the upper body parts, including the shoulder and the full face features. And at the bottom right, it can detect the full body pose, including the leg. In the design space, we broadly categorize them into three sensing dimensions: the near device, around device, and surrounding device. And in each sensing dimension, it can sense different things, such as handedness, the body posture, or the dangerous object. We also enable use case and applications by leveraging the sensing dimensions. Some use case leverage only one sensing dimension, while some use case leverage 2 or 3 sensing dimensions. Indeed, there are many related works, so we made a table to include most of them here. However, we realized that none of them can enable an all-in-one sensing that includes all the sensing dimensions that we propose here. OmniSense can enable all of them using only one single sensor. First, let's take a look at near-device interactions. The first one is adaptive UI, which means the keyboard can adapt to which hand is holding the device, or expand when both hands are holding it. The second one is haptic interface, which means that the UI can fade in or fade out depending on the hovering finger distance. Next is back of device interaction. The index finger on the back can tap the device and slide to control the volume. Next is seamless mode switching. Depends on which finger is touching the screen. It can be a brush or an eraser. Using the knuckle to touch the screen summons the color palette, while using a stylus instead of finger will switch into a thin brush. Next is 3D finger interaction. The user can hover in front of the screen to preview some message. Next, we look at around device interaction. It can track the full body pose for controlling avatar. Perhaps it is useful for virtual reality environment. Next is face touch detection. It will provide warning to the user if the user touched her face, because this was done during COVID time. Next is around body interaction. By moving the phone near or far from the user, it can zoom in or zoom out of the map. By rotating the phone around the body, it can pan the map. Next is leg gesture interaction. It can be useful when the other hand is busy and the user can use the leg to perform some shortcut gesture. Next is attention monitoring. If the user doesn't look at the screen, it will dim the screen to save battery. Next is spatial gesture interaction. The user can use the other hand to perform a real hand throwing gesture for play some games, such as throwing a Pokeball. The next dimension is surrounding device. It can detect the approaching objects such as car. It can also detect the tangible objects for tangible interaction. It can also detect the color of the stylus to change the brush color automatically. It can also detect the hand pose of the other hand to change the drawing shape. Because it can see the surrounding environment of the user, it can also recognize the surrounding and provide context awareness, such as in a car. While inside the car, it can count how many passengers, and it can detect whether the seatbelt is not fastened or the hands not on the steering wheel. It can also detect if the driver is using smartphone, which can be quite dangerous. And it can also detect various in-air gesture for controlling the infotainment system. For implementation, we tried different hardware, and finally we settled on a smartphone with a built-in 360-degree camera. However, there was no API access to the raw image, so we have to use screen capture method. Since there are no existing model for tracking hands and fingers from this unique camera point of view in our setup, we have to collect data and train neural networks by ourselves. For body parts tracking, we used existing libraries such as OpenPose. We conducted a baseline technical evaluation. I will not go into details here, so please refer to the paper. In short, for the handless task and the active finger task, the results are very accurate because these tasks are relatively simple because of this unique viewpoint where the hands are always at the middle of the camera view. For 2D fingertip tracking, the average error are under 3 mm, while for 3D fingertip tracking, the error are higher at 4 to 8 mm. We also conducted a preliminary user study to gather feedback and insight about our techniques. We invited another 10 participants to try our system, and they tried 13 mini applications spanning the 3 sensing dimensions, as shown here. In short, the results are: applications related to the body and surrounding are well received by the participants, but less so for the applications related to the finger interaction near the device. The finger sensing techniques are rather gimmicky, as mentioned by some of the participants. In the paper, we also have discussions related to privacy concern, battery, and others, so please refer to the paper. In conclusion, we have presented OmniSense, a design space covering a broad range of input sensing and interaction techniques for mobile devices enabled by a single built-in 360-degree camera. We demonstrate how this single sensor is capable of enabling various compelling use cases and applications. We conducted a baseline evaluation and preliminary study. We hope that this exploratory research showcased the potential of 360-degree camera for enabling novel interaction techniques for improving mobile interaction.